Okay, the problem is search in rotated sorted array. That is the problem statement. So let's say could we find anything like it is a sorted array but rotated. Search have to search the element. If it is element present, then it is to return the index position. If not present, that is -1. By this time, I guess you know what is a sorted and rotated array. So if is the example is a sorted array, it could be rotated by left index or 3 index. It could be looks like this. So it is sorted by rotated. You have to find out the index. If it is not present, it will return -1. Simple. So to say like length is 5000, so it could be done big of 1. Like you can see, let's find function and it will be done. But this is not our target. Target is big of log n. Log n can be achieved only by binary search. Simply I have to apply binary search here. So let's take an example. I will take these two examples and explain how could we do that. Okay, so let's write the function and I'll keep writing the thing and explain like how it is possible, like what are the logic we should think of it. So I know it's a binary search, so let's write a function. So let's find function. What I have to function, the one nums array is given, I guess nums array, and one target t. I'm writing target as t. These two are given. Okay, I'm writing the thing. So let's write a typical binary search case. So typical binary search means I need a left, it is 0, and right, that is nums of length -1. Typical binary search, length -1. And after that one typical for loop, while L less equals to R, this for loop will run. And inside the for loop typical cases, like if ARR of L less than my target T. So this is one case. This is one case. If else if that is not the case, I'll explain the like what will I'll write the in mid like inner thing later and writing the structure of the binary search. Not what why I'm writing L. I need a mid, right? How could I forget to calculate mid in our binary search? So mid is nothing but let's say mid is L plus R minus L divided by 2 is mid. So after that I need if statement. If my not t, if my mid of t, if my mid of t is less than this, if my mid of if my mid of ARR mid is greater than t, then one case, else otherwise if it is equals to 3, if it is equals to 3, then we can directly return the current mid. That is my answer. So return my index. Index means yeah, it is index now. It is actually mid. That is my current index position. Will return. Otherwise, my loop will end. If the loop ends, that means I didn't find anything. That means I didn't find anything. So return -1. So return -1. Return -1. So I didn't find anything. Okay. So this is my typical structure of my binary search. Correct? Okay. So when this is possible and when what we write like when this kind of case appears, what if it is mid value? If let's say mid value, let's say this is my assume this is the part of I. This is my mid. If my target is 5 and mid value is less than target, what I do? Left should be mid plus 1. That you usually write. That I write left equals to mid plus 1 In this case, usually write this thing. Or in this case, what we could write, if mid is greater than case, I write r equals to mid minus 1. Simply write this kind of thing. But this is a normal case. If array is not rotated, so in the given array, you can say it is a fine. It is actually, it is given like it is not a kind of, not a case like when it is not in sorted and rotated. It is not. It is actually uh, overruling that condition or breaking that condition. It is not like that. It is obvious. It is given that condition is given. The answer is ascending array that is possibly rotated and you can say rotated. So if it is not rotated and all values as norms are unique as well. Okay. So what is the case? What is the case? What I am saying. So what I am saying, like if it is not rotated, then what is it is sorted? So sorted means I can simply apply this rule. So when I can say like it is not rotated. If it is rotated, if you notice, if it's rotated, this right's value is actually less than my left side value. So if it is not rotated and all elements are unique, that means what? My left side value, if it is not rotated, this could be my actual array actually. So this is as well as index position and as well as my actual array. If it is, this is the actual array, and after the rotation, I get this one. I get this one. Rotate left like many times, and if we rotate 3 times, it come here. So this is the rotation case. This is actual array. If it is my actual array, then how could I know like if it is an actual case and it is not rotated? So if it is my left side is less than my right side, then it is my actual array. So then I can apply this rule. So that's why I'm just simplify this case. Like if my found one any case, like if it is after some kind of like means division, where divide by half, then half. Let's say we divide this thing as half, then let's say divide this thing is this half. Okay, so that means in this half. So assume I have to calculate zero, like zero, right? So if I don't know the logic, what I have to do? So if I find a zero, I will first check and mark this thing is half. I will getting this zero is present in the right side. So again I will half the element. I can see zero is my right side again. Okay, so I have to right now find in this window, right? Now if you notice in this window, for this case, in this window, this case, this is my actually sorted array. This part is my sorted array. So this could be a possible case where I can get a sorted array already. That my what is the numbers present in my current portion, one is a current piece is already sorted. It could be a possible. At that time, I can apply my normal sorting rule. That's why I'm saying when I can say like that, if my left is less than my right side, then I can say it is a normal case and I can use normal scenarios. Why I say normal condition or normal case, like this is a normal cases, right? Why I'm saying normal cases, I will come it later. You will understand. Okay. So let's see. Before that, let's write down the what is the normal case. The normal case is if if my ARR of left is less than ARR of right. If that is the case, then this is my scenario. This is my scenario. Okay. I'm writing here because it will take too much spaces. So here also I have to write the same scenario. I have to write the same scenario here as well. If that is the case, this is normal case. So write will here. Now let's find it out. What are the right now? If it is rotated, then what could be the possible cases? What could be the possible cases? So I am not thinking about invalid case like my item doesn't present right now. Let's find the item what is present. Let's focus on that. Let's we think about what is not present. So first thing you have to notice, one special thing you have to notice in the sorted but rotated array. What the special thing is, so if it is rotated, this sort array actually divided into two sorted array. Two sorted array, you can see every time you do. the two sorted array. So if it is a two sorted array, so please remember first portion of the first sorted array, first sorted array could take the maximum space of this array, and second sorted array it could take the smaller amount of space in the entire array. Here first sorted array taking the smaller amount, second sorted array is taking the maximum amount. Okay, why I am saying that I'll explain you in a minute. So please mind it that another possible case is it could be 50-50. It could be 50-50. So actually it could be 50-50. But in that case, it will be different thing. We'll come that thing later on. But it could be 50-50. But this thing is it it can take maximum, like first sorted array can the maximum position, or second sorted array can get the maximum position. Okay. Now let's focus on this case. When my mid is actually less than my t. Actually less than my t. If mid is less than my t, if it is 50-50 case, then this case doesn't appear. If it is 50-50 case, target is 50-50, so it cannot possible. So if I write that thing like 50-50 case, like 0, 1, 2, 3, 4 and 5 and 6, 7, 8, 9 and 10, if could be the case, or then you can say this mid is not actually possible. Or if it is 10, if it is move one time, then this is the maximum element I am finding. So it is very less likely this is going to happen. Or this case will be solved. If this is the case, we can say 10 is smaller than my mid, right? So then we could find out what is the relation. We will find from this case as well. This is equivalent to this case. You can find it out. Okay. So let's see. So first, let's see the first case. So if my fast sorted array taking the maximum position, if my fast sorted array taking the maximum position of the array, and my mid is less than 10, sorry, mid is less than my target, that means my target obviously present my right side, because fast sorted array contains the maximum elements of the array, and here middle also contains the maximum element of the, like most likely maximum element of the array, correct? So that means whatever my target, it could be present at it should present by the right side. Hope you understand. So here only it is present to the right side. If my second sorted array takes the whole place, then mid should be like it belongs to minimal numbers. It could be 0, 1, 2, 3. If you notice, these are the minimal numbers, like smallest number on the sorted array. So that time that my target could be present at the right side or could present at the left side. Assume here target is 9, here target is 7, sorry, here target is 10. So 10, in this 10, so what I am saying here, target is 10. So this is my fast sorted array taking the maximum place, and that's why my mid is less than my target. That means it should present on the right side. You can see 10 is right side, but here it is 10. So here 10 can present on the left side. 10 can present on left side. Okay. So if it is 7, say for this example, take target equals to 7. Take target equals to 7. If it is 7, then it is present at the right side, or if it is 8, it present in the left side, correct? We don't know where it could present, we don't know about that. It could present anywhere, any place, right? It could be present left, it could be present right, we don't know, correct? So what could be the our cases? Or can I modify small, then I can show you the whole cases. Okay, so if I change this one, the two places 1 and 2, this is the my case, or 7 is also fine. Yes, I can put 1 here and put 2 here. So okay, and if I remove 7 from here, or not 7 from here, I can remove 8 from here. Yes, so see here, This is a good case right now. So assume we are finding here target is 8. If your target is 8, in the first case, as I told you, like fast array taking the fast sorted part taking the maximum place. So it is obviously right side. This is obviously right side. If it is 8. So if it is 8, here it is present also right side. When second sorted array taking the maximum, it is also present in the right side. Okay. And if it is 9, see here in the first case, fast sorted array taking the maximum place, and this is my observation. How could I know it's a fast sorted array taking the maximum place? I'll think it later. But this is the observation, like my fast sorted array taking the maximum place. And here it is 9, it's present at the right side as well. But here, if it is notice, it is present at the left side. So it is present in the left side. So there are two possibilities. It could present left side or right side or the left side. Okay. So now my question arises: how could we know like whether my fast part is taking the most of the sorted part is taking the most of the array? How could I know? So that now you have to observe. See here, this 7 actually greater than my last item. What is the mid item? Mid item is greater than my right item. So middle is greater than my right. That means this is fast portion is taking the most part. Middle is getting the right. Here if you notice, middle is what? 3. This middle is smaller than my right. The middle is smaller than my right. So that means second half taking my fast portion. Okay. So fast case. So what can I do? So every time it could right and it could go left. Two possibilities. So if I find out the condition when it could go left, then I can only pass this thing onto that time to left. Other times I can pass the thing to the right. Other time I can pass the thing to the right. Correct. So for this case, so when I find out that my fast sorted like 8 item present in the left side, that is my target. How could I know? So first for that I need to distinguish what is my case, like whether my fast case, like what is my fast sorted array present in the maximum place or second sorted array, second sorted part taking my maximum place. For that, this is my observation. Like mid value, if it is greater than my right side, then it is uh, if mid value is greater than my right side, then my fast sorted part taking the maximum place. If it is smaller, then second sorted part taking the maximum place. Correct? So this is the. So if you notice this thing, this is also greater than left. So you can also check with the left. But there was a catch actually. There was a catch. I will take at the very end. There was a catch. For right now, please compare always with right. You can see like this 7 is greater than left or right. So you can argue with me like, so instead of writing my condition like mid should greater than my R, I can condition like mid should greater than my left, but I can also argue. So there is a catch. That's why I'm saying there is a catch. I'll tell you later. For right now, I'm comparing with the right only, not the left. Okay. See, so fine then. So what my first condition is when I can, my target is when I can know my target element position in the left side, right in the left side. So in that case, I'm to first question is if ARR of fast observation, if if my ARR of mid is actually smaller than why smaller than, because I know like if it is smaller then second part uh, and in this case second sorted part will take the maximum side, and only in this case I can go to left side if my mid is less than target. This is the thing for which I am calculating right now. So for now, if mid is less than my target, so ARR of, why I am directly writing less than, because all items are unique, so it doesn't matter. Less or equal you can write. So right now, if it is less than my target, if only it is the case, so if it is only it is the case, so can I say if it is only case? See, for 9, I can say here. But for 7, so for writing this condition, I'm discarding this one. I'm discarding this case. So now in this case, so I am from the checking this condition, I know this is my second sorted part taking the maximum item. Now here there are two possibilities, right as well as left, right as well as left. So when can I know, like if it is present in the only left side, it is present in the left side. So if my target is, what is the target? What is the element present in the left side? If that is less or equals to my target, then that means it is present in the this side. How can I say that? If we say right sorted rotated array, right? So by default, there is a one condition that is always true. That is left of array is greater than error of middle, error of right actually. It's by default it is true always if it is a rotated array. So if my target, my left side of that target is smaller or equals to my target, that means what? It could, like, it cannot present in this area. It cannot present in because this is if my second part, if my second part take the maximum place, what is present in the first part is actually the most larger elements in the array. Okay, and that larger element is smaller or equals to my target. That means it should always present in the first part. It is always present in the first part, not in the second part. Hope you are getting it. So if I write 8 or 7 or 6, or let's say 6, 6 is not smaller than this element. This element is not smaller or equals to 6. Okay, that means what? It always present in this right place. So I'm writing another condition is that and if ARR of left is smaller or equals to my target. If this is the case, then I can simply say, like, yes, in this case, my target present in the left side. And what do we do when target is present in the left side? We put our right side of this right to the mid minus one. That we do. So let's write this thing, and if let's write the case here directly. So if that is the case, and this case is also true, then we will do what? We will do r equals to mid minus 1. That we do half of it. And if that is not the case, that means it will always present in the right side. This is the case. So this is the only one condition it present in the left side. In that case, it is present in the right side. That's the right. So if it is not true, then else it will present my tail will be mid plus 1, because if it is present right side, then mid plus 1. That we do. This is about my the case. Hope you understand. Okay, so this is the case. So let's say this is the case when we can traverse. So we will do the dry run after that. Okay, now let's do, like, what is the other case? Other case in the sense when is another condition is there. Another condition means this condition. So there should we have to write one else if as well, because if this is the true, then it is coming here. Then if it is not the true, then it will come else if you write else if here. Okay, so here these two if else actually different. Okay, so here actually use an else condition here. Don't directly write this if else. Don't directly write this. So it should be inside the else. This else. If you directly write this, then it will create a problem. This is the first case. What is the second case? Second case will be the exactly kind of similar. If I remove this case, second case means this case if mid is greater than my target. So as you know here in this target, what is my target is, let's say 0. Okay, if 0, if it is greater than my target, okay, so it could present on the left side and it could present in the right side as well. Here let's say in this, let's say target equals to 1. Okay, in the first case we can say it can present in the right side, and if again in here it is present in the right side. Let's say target equals to 2. Here it is present in the left side, but it is always sorry, it is not right side, it is left side. So if it is 2, here it is present in the now left side, but it is also in the left side. So what actually I am meaning, I want to mean, as previously what we noticed, if my fast sorted part is taking the maximum part and medium and then it is highly case if fast sorted array take the maximum part and the mid value is less than my target, then my target value always present in the right side. But here this is the opposite case. That's the opposite case. If my fast sorted part is taking the maximum part and my and my target mid is less than, if mid is greater than the target, then it could present on the left side, it could present in the right side. Two cases. Here you can see second sorted part is taking the maximum place. In that case, my in that case, but if my mid is greater than my target, it will always present in my uh, it is always present. What I actually doing, it is always present in my right side. Why I taking the if it is greater than a target, so it is always present in the left side. It will always present in the left side, not right side. So target 1, 2, anything. If it is 4, then you can say here 4. That if I say it is 3 or 4, if it is 3, then it will again come to the else and return the mid, right? If it is 4, then it is kind of overriding or discarding the condition, like this is this condition is discarding this condition. So these are the two things. So we notice again one thing. So if my fast sorted part is greater than, if my fast sorted part is greater than my is fast sorted is present is taking sorry is my fast sorted part is taking the my most taking the many like most spaces in the my array, then if and in that case if my need is greater than my target, then there are two options and left and right. Okay, but if my second sorted part take the maximum place, then there is only one option, that is going to left. So better to find that right condition, then so it could go left and right. Other cases, like if we find out the specific right condition as we did earlier, then we can find write that condition right like that way, it should go to right. All other cases it go to left. So when we go to the right, so first we have to discard. First we have to see when my first sorted part is taking the maximum place. So there are two ways, you can observe or you can do the counter positive. Like earlier we saw if ARR of mid is less than of ARR of R. Earlier case I am talking about, this case. If this is the case, then we notice that in this case my second sorted part taking the most cases. Okay, right now I need what? I need, when the condition I need this thing. Okay, fast sorted part take the most cases, most spaces. This will be the exactly opposite. So right, exactly opposite. Then this is the case. Similarly, like you can say the left case, you can consider the left case as well. Correct. So I will come. I told you I will come. So I will tell you one counter positive case at the like one. You can take L, but there is one catch, right? You have to tell, consider this as the last. So this is the first case. If I write this thing, that means my fast sorted part is taking the most cases. Now I discard this part, discard this case. So if that is the case, now I have to know like when it is, will it go to left side or it is go to right side. Earlier we noticed, if now when it could present at the right side, so I need the right side. If my right part is greater or equals to my target, if my right part is greater or equals to my target, then we can directly say if my okay that is the case, if my right part is greater or equals to my case, then I can say like it is present in the left side. If it is 0 1 anything, or if it is 0 1 or 2, in that case, if my assume this 2 is present in this case, okay, this 2 here, then that is the case. If that is the case, then I am finding 0 1 2 anything, and if my right value is greater or equals to my the target, that means it is present in the right side, otherwise it will present in the left side, correct? So what I actually mean to say, this one is actually greater than my target, and this also is greater than my target. That means it is present in this area, greater or equals to. So that means it is not present in this case. So the two cases and at ARR of like what I said, right, greater or equals to is greater or equals to my target. And that is the case, my target is in the right side. And what do we do in the target case? If it is in right side, then we will move my um, AL equals to mid plus 1. We'll do this thing, correct? Okay. And write the same coordination here. So I'm taking this case and writing the same coordination. All other cases I can go to the other side. So let me write it down. So as I told, so this is the opposite and this is the case. So this is greater than the case and right is greater or equals to my target. Then I will simply say I will just interchange the positions. So if that is the case, we know like mid is greater than my this. So I do like mid L equals to mid plus 1. Otherwise, in other case, R equals to mid minus 1. All other cases. So if I do right side, if my target is present in the right side, then I do, sorry, if the target is present in the left side, then I do R equals to mid minus 1, half, cut the half. This is I do. And if you believe or not, this is the final solution. Okay. So this also contains our edge case, like if doesn't present, if my item doesn't present, this also covers here. Okay, let's do the dry run. Okay, so let's say 9. 9 is present, let's say 11. So 11 doesn't present in first and second case. Let's say first case. So first case 11. 11 is less than my mid. So right now this is L and this is R. This is the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I told you earlier, this is the index as well as the actual sorted array. Okay, whatever. So I am finding the 11. 11 is not, what is the condition? It comes here like mid is 7. 7 is less than my case. If my left is less than right, then it is a sorted. If it is less, no, it is not less. In that case, it will come else condition. Else, if I mid is less than my R, yes, it is less than. Is it less? No, it is not less than my R. So it will say I'll do L equals to mid plus 1. So L equals to mid plus 1. I'll do that. So L comes here. Now what will be my new mid? New mid will be 6 and 10 and this one 8. So again I am finding 11, right? If you remember, I am finding 11. If 11 in the case, if 11 is the case, um, then mid is again, mid is less than my target. Okay, fine, mid is less than my target. and it will is it case like if left is less than r? No, it's not the case. So then you come to else. If mid is less than my r? No, it is not the case. So I will go. That means uh, it present in the right side. So it will do l equals to mid plus 1, and l comes here and r go here. And what will be the in this case after that? Mid will be nothing but my 9 only. Like in this case 9 and 10, 9 will be the mid. In that case I will do the calculation. Mid is there. 9 is it, what is the index, what is present? 0. 0 is error of mid is actually less than my target. Okay, less than my target. If it is the case, yes, this is the case. L and R. L is smaller than error of L is smaller than error of R. That means I will do mid. This is a sort. I can think it's a sorted array. Now I can move L equals to mid plus 1. So L equals to mid plus 1. It will come here. It will come here. Or L and R both are the same actually right now. Mid will be the same as well. Mid will be the same as well. So what is the case? Is it what is the case again? This is nothing but 1. This is again smaller. If it is again smaller, then it will come here. If it is the case, if um, left is smaller than r, smaller or equals to, you can also say. But if it's not the case, so if it is smaller or equals to, you can say equal, actually equals to, you can put it here as well. So in that case it comes here, else comes here, doesn't matter actually in this case. In this case what I'll do, like right now it will try like if mid is less than r, no, it is actually equal. So not the case, then l equals to mid plus 1. So l will mid plus 1. Whenever it will do mid plus 1, now you can say this condition is overridden. This condition is overridden. L not less or equals to r. So this is the case. So either you can write equals to here, or doesn't matter. It will take care of that. Okay. Okay. Similarly, you can test for here as well. Like if it is not, if it is present in 11 here or not, you can present that. Check that way. Like I'm not writing it down, but you can find it out. Or let me show you as well. 11, I am finding the second array, left and right. Sorry, left and right. So left is actually, this is smaller than my right. Sorry, mid is what doing again. This is the mid. This is mid. So what I am getting, mid is actually smaller than my, again smaller than my target. Fine. Now is it the true? No, it is not true. Now it's same. If mid is less than my r, mid is less than r, it is true. And if my left is smaller and equals to my target, is it the case? Yes, my left is smaller equals to target. That means this should present in this half. This should present in the, if it is present, it should present in this half. So right should move in this place. Here, mid minus 1. Again, what will be the mid? This is the mid. Similarly, you can say yes, this is actually 0, and it is smaller than my target, and it will come to else case. Here mid is also less than my right side. So and my left is smaller than my target. Then again that right will move to the mid minus 1 here. So again mid will nothing but this one, and if that is the case right now, both are same. Like if L is smaller than R, so normal case. So in that case, if mid is less than my target and if it is also true, then I'll move this L to rth place. Both are right now point to the same place. So if it is pointing to the same place, if it is pointing to the same place right now, now this place also point the mid. This is also the mid. In that mid, so mid is again smaller. Mid is smaller if L is less equals to R or something. So it is less than, no, else it will come else position, and we will say like mid is less than R, no, mid is not less than R, then L equal to mid plus 1. So it will go outside of the greater than R. L becomes here. In that case, my L is not less equals to R. This thing violates. and it will return -1. How? This is how it should work. Okay. Hope you understand the thing. This is you can try to diagram of other cases, like all other possible cases. This is you can try and test it out. Okay. So this is the case. What is the time complexity? It is a binary search. So big of log n. Okay. And space complexity. Are you taking any extra space? No. It is a big of 1. Okay. Another thing is like when I was solving this problem, when I'm finding this kind of condition to separate my first sorted part is taking maximum part, or second sorted part is taking maximum part or not, I am writing these solutions, right? These cases. Correct? So in these cases, you notice when my mid is less than error of r, so mid is less than error of r, it is also less than error of L as well, right? When mid is greater than my error of r, it is also greater than error of L as well. So that time you can argue like instead of less than greater than error of r or less than error of r, I can write directly L, right? You can argue with me, correct? So you can do that. And even though in this place you can directly put L as well, there is no problem. But if I see like there will be a problem if you directly write this case. Instead of this line, if you write error of mid is greater than error of L. Apparently it is seems fine. Apparently it looks seems fine, but it will be a problem. So for this case, just take a simple example. If you write this case and take a simple example, 3 and 1. What is my index position? 0 and 1, correct? And this is my left, this is my right, correct? So in that case, my mid will be what? Mid will be this one, mid. So and target, assume target is my 1. So what will happen? See my mid. So it will come this place like error of mid is greater than my target. Error of mid is greater than my target, correct? So target is 1, mid is greater than target. So it will come this place. It will check if error of mid is greater than my error of 1. It will say uh, error of error of not 1, error of L. It will ask like whether this thing is greater than my error of L. So here you can see if mid is greater than error of L, is it? No, it is not greater than. It is actually equals to error of L, because mid and L are both are same right now. Okay. So what we will go, it will becomes false. That time it comes in position, and what we will do, R will mid -1. So R will be mid -1. So R comes, R will point this 3 only. So see here, right now there is no way I can reach to 1. Right now there is no way I can reach to 1. So there's a reason I told you always point to R, because whenever like is less likely chance like mid and R cannot actually stay in the same place. Mid and R is always difficult a different place. What I am saying actually, see this case. If it could be on like take any example like 0, 1, 2, 3, 4. Okay. So in this case, this will be like I'm taking a generic example L and this is R. So this will be mid. After that, L will come here, L will come here. Then say let's say then if these two are the case, then mid and R can point to same index. Sorry, mid and L can point to the same index, but mid and R cannot point the same index. Not any time. It is only possible if L and R point to the same index. Then only a mid can point the same index. Otherwise, it is not even possible. Not even possible, because like whenever we are getting, if it's a odd number index, if it is a odd number index like only 1, 2 and 3 is present, odd number index is there, then middle point here between, okay, less than r. If it is even number index 1 and 2, this is L, this is R. So in this case mid will point this one, because why? Because it is 0 and 1. So what we do for finding 0 plus 1 by 2, that is 0.5. We take the down one, the floor value. That's why this 0.5 becomes 0. So AL and R may converge, but sorry, AL and mid may converge, but mid and R cannot converge anytime. That's why if you are taking this condition here, you have to write less equals to. That is the condition. If you write L here, it will write. But in this case, you can directly write ARR of L. It will not create any problem in this case. Okay. Hope you get it. This is the reason I'm saying like always check with the R, because mid and R never converge, but L and mid it may converge, and once upon a time it will converge at some time. So that's the reason. So if you want to using L, you have to check whether it is equal or not. If there is any case appear when we can see L and mid come same or not. So earlier also I feel like actually I came to know this thing after failing one test case, and this is the exact test case I felt. Earlier I was instead of R, I was using L actually. Both are L. That time it is fail at 3 and 1. This same exact test case. And there from there then onwards I came to know it will this is the case. Like why that's why I'm finding why it is failing. Then I can see like mid and L can convert. That's the reason it may fail. Okay. So there is actually another way to solve this problem. Let's say this is approach 1, and I'm taking this example, these two example, copy. Let's solve approach 2. This is a very kind of like very interesting approach. Time complexity will be same, no other changes, nothing. But approach is right, very cool. So this is my current position, correct? So as I told you, this is my array as well as corresponding like original array as well as my index of that array. So that's why I'm taking 0, 1, 2, 3, 4, 5, 6, 7, 8. So after rotation it becomes this. After rotation it rotation this. So if you find my rotation place, so this is if I how many times this array rotated? 1, 2 times it is rotated. So what is index place? 2. Okay. So what is rotation? Rotation, how could I find the number of rotation? Number of rotation I can find what is the smallest, what is the position of the smallest item in this array. That is the number of time it is rotation. Correct? So if we consider this one, what is the number of rotation? 9 times. 9 times. How? So 1, 2, 3, 4, 5, 6, 7, 8 and 0 is 9. So 9 time rotation. So if I want how so number of the smallest position in this rotated array is my current rotation. Okay, sorry, rotation of this array. Okay, so how could I solve right now? How could I solve? So how could I solve this thing? So notation. So let's see what is the case. So let me write the normal generic case again. So when we write generic case in the sense, copy and paste. Here, these are the things actually you don't need. These kind of things we don't need anything. It is a very kind of surprisingly um, satisfying approach. So what do you do? So we came to know like find rotation also. We need a find rotation. Okay. So one function I need find a rotation. Okay. As I told you. So let's say ROT equals to find rotation. In this function, let's say rotation I am actually want to find. It is not selected. Rotation, number of time it is rotated. So how could I know? I will say let's say find rotation function. Rotation function. I will pass nums here. So it will find rotation. It is nothing. It will return me the minimum index of minimum item of this rotated array. And how could I find this? I have explained this thing in 153 LeetCode 153. Okay, please check. No need to see my video. You can, because it is very lengthy. You can see any other video. The exact same function I will use. Okay, you can see any other video and just know how it works and how I can find the minimum of this 153. Sorry, if you find the smallest item in this case. So this is I need. So rotation I can find it out. Okay. Yeah, and if you want to watch my video, I'll give that description in the video link in the description. It's up to you. Now what I will do now, see the observer. See what actually my case. What is my left and right? This is my left. This is my right. Correct. Okay. What is my mid? This is my mid. Mid value is what? Mid is what? Mid is right now index is 5. What is my rotation? Rotation is what? 9 line. This I'm talking about this one, right? Talking about this one. So how many times it's rotated? It rotated for 2 times because my smallest item present in the second index, that means it is 2 times rotated. But 2 times rotation. So what is my mid value? 5. What is my rotation value? 7. Okay. And uh, 7, right? So what is my ac actual value? So what do I mean by actual value? Actual value I want to mean like what is actually present in the fifth index. If it is not sorted, like if it is not rotated and if it is actually sorted, what should present in the fifth index? So fifth index it should present five as well. 5 only it should present. So can I get directly check? Can I get anything here? 5. Can I get? So 5 modulo 2 is nothing but what? 7. This is 7. And if I modulo it divided by length of the array. So what is the length of the array here? Length of the array is 11. 11. Okay. So what is the case? 7 is the case. So if I do this, see here, 7 it is index. So see what is present in the 7th index? 5. So this is nothing but my actual, it should be my actual mid value of my unrotated array, just sorted array, not rotated array, non-rotated array. Okay, just in sorted array. In the sorted array, this is the sorted array, and then what should be the value present? 5 in the mid. What should the value of that should be the value in the non-rotated array? 5 should be the value. See here, 5. So now I can compare my 5 with my target like we normally do. So instead of taking that kind of heavy expression, I can simply find it. So not only this one, you can take any index. Let's say I'm taking this 8 index. So what should present in the 8 index? 8 should present in the 8 index. How could I know? Like 8 plus 8, 8 plus 2, nothing but what? 8 plus 2 is 10, and 10 modulo 11 is nothing but what? 10. So see what is present in the 10th index? 8 only. So that is the current value. Like it is a value which should present in a not rotated array in that particular place. So not only this thing, take this array, take this one, take any example. Let's say take many examples. Like let's say 9. What is the 9? The ninth index in non-rotated array. In the ninth index, 9 should present, correct? So let's say, can I find this 9 from my calculation? Let's say 9 is there. What is the rotation here? It is rotated by ninth place, right? So 9 plus 9, it is what is 18. 18 modulo 11. What will be 7? So what is present in the seventh case? We can say 9 is present. So instead of checking what is currently present in the mid value, I am checking what is the actual mid value. What is the actual mid value? Like what is the actual value present in the mid index? I am checking this way. How I am checking? Simply by using this formula. Got it? So you can use, this is a kind of observation. You have to do too much observation. After that, you can find this thing. So you can, instead of taking what is present in the mid index, I am taking what should present in the mid index in the non-rotated case. So if it is not rotated, then how it should looks like? It should looks like by this thing, na. So I am repeatedly saying this is I taken a very special case, very case, so that this is the actually index position of the array as well as this is the value of the array. So index is actually representing the value of the array if it is non-rotated. So if it is non-rotated, then for us it is easy to find. Just finding the binary, just finding the item using the binary search, right? So that's why I'm finding. So instead of finding what is the proxy value, I'm saying the proxy value. Proxy value is what? Like after the rotation, this is a 7. But what should be my actual value? Actual value is 5, right? So can I know? So take this example, like right now it is 5 in the fifth index. What is value is 7, but what value should present actually in non-rotated value? Non-noted array, what should present? It should present the 5 only. So if I calculate 5 plus 9, what is it? 14. 14 divided by 11, that is 3. What is the present in third index? See, my actual value. Actual value that should present in a non-rotated array. So this is how I can calculate. So instead of calculating directly checking what is present currently mean, what I am checking, what is actually what should actually present in the non-rotated array. So then it's a binary search, normal binary search. Okay. So I no need to check my mid. I am checking real mid. So let's say I'm checking new thing. Let's say real mid. What is my real mid index? Real mid is nothing but my mid plus my rotation modulo nums of length. So here I am taking one array, one variable. It will be easy because every time calculating length doesn't seem good. So I am taking one n. Let's say n equals to nums of length, and here also I am using n minus 1, n minus 1. In calculation I am using n. If that is the case, this is normally binary search, but here I will not compare with the error of mid. I will take the real mid. If it is less than target, what do we do? If it is less than target, we simply remove our R value. Mid is less than target, right? So update the left value. So N will be mid plus 1. Here also, this is a simple binary search, not mid. Real mid greater than T. Real mid greater than T. This is what we can take. Real mid, and it will be R equals to mid minus 1. So this is as simple as that. Normal, this part is nothing but a normal binary search. No everything. Only funda is this one. Only funda is this one. And finding the how many times it's rotated. So it is also takes big of n time. So it will take a slightly higher time because why? This takes big of log n actually. Log n. And this one takes big of log n. So overall it is big of log n. If time complexity it is big of log n. But if you think logically, it is, and stress zone is big of 1, obviously not taking any extra space. But what is the case? It is not only log n, it is actually log n plus log n. So it is 2 log n. It is taking twice time than the previous example. So but the thing is the approach is really good. That's why I'm showing you. Compared to this one, this is actually the best approach. This is not that much of efficient. This is the efficient. It's calculation heavy, but it's efficient. This is calculation is very easy, but it is not that much of fast than this one. Okay. Hope you get it. And as always, if you find any mistake in this video, please let me know so that I can rectify. And if you find any useful information on this video, please also let me know. Thank you. Bye bye.